This is question 6 from the 2010 paper, and this question is about gold leaf. The question begins by describing how gold atoms crystallize in a cubic arrangement, which is shown. The gold atoms are assumed to be spherical and are shown at half radius size rather than touching their neighbours. The diagram shows a unit cell which can be built up like building blocks to form the lattice structure of gold. In part A of the question, you are told that Avogadro's constant is 6.02 times 10 to the 23 per mole, and that gold has only one isotope which has a relative mass of 197. You are then asked to use these facts to calculate the mass in grams of a single gold atom. To answer this question, you need to know two facts. The first fact is that 1 mole of any element contains Avogadro's number of atoms, and the second is that the mass of 1 mole of an element is equal to the relative atomic mass of that element given in grams. Therefore, we can say that if the relative atomic mass of gold is 197, then the mass of Avogadro's number of atoms, or 6.02 times 10 to the 23 atoms of gold, is equivalent to 197 grams. And therefore we can calculate the mass of one atom of gold as 197 grams divided by Avogadro's number of atoms, which is 6.02 times 10 to the 23. And if we do that sum, we calculate the mass of an individual atom of gold as 3.27 times 10 to the minus 22 grams, and that answer is given to 3 significant figures. In the next part of the question, you are told that the cube shown in the wireframe in the figure, which has now been highlighted in red, has its corners at the centre of the atoms occupying these corner positions, and that the faces of the cube pass through the centre of the atoms found in the centre of these faces. In part B, you are asked, by considering the fraction of each atom actually inside the unit cell, to use this information to calculate the number of atoms within the unit cell. This question really involves you looking at the diagram and trying to picture the unit cell in 3 dimensions. If we therefore look at the cube, if the faces of the cube pass through the centre of the atoms found in the centre of these faces, then we know that each centre of each face must contain a half of an atom, and so we can represent this by adding a half to each of the centres of each of the faces of our unit cell. Each corner of the unit cell contains within it 1/4 of 1/2 of an atom, which is equivalent to 1/8 of an atom, and so we can represent this by adding 1/8 inside each corner of the unit cell. Knowing this information, then, we can very quickly add up that the total number of atoms inside the unit cell is equal to 1/2 of an atom on each of the 6 faces, plus 1/8 of an atom on each of the 8 corners, which, if we do that sum, we can find that the total number of atoms inside the unit cell is equal to 4. Part C of the question now moves on to using trigonometry to calculate different dimensions of the unit cell, bearing in mind that the atoms are in contact across the diagonal of a face of a cube. In part I of the question, you are asked to find an expression in terms of the radius of the gold atom R for the length of the unit cell, which can be represented by the distance between the centres of the atoms A and B. To help with this calculation, I've sketched out a simplified version of the unit cell. If we look at a single face of the unit cell, we know that if it has an atom at the centre of the face and atoms at each of the corners, with the atoms touching across the diagonal. If the radius of a gold atom is given by r, we can therefore see that the distance diagonally across the face of the unit cell is 4r, 2r across the central atom, and then r at each of the corners. To calculate the length of the edge of the unit cell, the distance AB, we need to apply Pythagoras' theorem. Pythagoras' theorem states that in any right-angled triangle, the square of the hypotenuse, which is the longest side, is equal to the sum of the square of the two other sides. So in this case, as the unit cell is cubic, and so all the sides are equal, we can say that the square of the hypotenuse, which is 4r, is equal to 2 lots of the distance AB squared. Multiplying out our brackets then, we say that 16r squared is equal to 2ab squared, and so we can see that the distance AB is equal to the square root of a times by r, which simplifies to 2 root 2r. In part 2 of the question, you are now asked to use this value to calculate the volume of the unit cell. Since the volume of a cube is equal to the length of any one edge of that cube cubed, then the volume of the unit cell can be represented by the distance AB cubed. Substituting then the value for AB, which we calculated in part I, the volume of the unit cell becomes 2 root 2r all cubed. So multiplying out that bracket, 2 cubed is equal to 8, root 2 cubed is equal to 2 root 2, and then r cubed is r cubed. And so our final answer for the volume of the unit cell is that the volume of the unit cell is equal to 16 root 2 r cubed. Finally, in part 3 of the question, you are asked to give the length of the unit cell body diagonal, which is the distance between the centres of the atoms A and C. In this case, we need to look at what distances we already know and then use trigonometry to calculate that distance AC. So if we look at the unit cell, again in a simplified form, we want to find the distance AC. We know the distance CD to be the length of the unit cell, which is 2 root 2r, but we cannot use our Pythagoras at this stage because we don't know the distance A to D. However, we can use Pythagoras because we know the distance AB and the distance BD, and so we can apply Pythagoras to that purple right-angled triangle to calculate the distance AD. So looking now, the distance AB is 2 root 2r, the distance BD is 2 root 2r, and so we can say that the distance AD squared is equal to 2 lots of the distance 2 root 2r squared. So multiplying out our brackets again, we've got 2 lots, 2 squared is 4, root 2 squared is 2, and then we've got our r squared. So we can say that the distance AD squared is equal to 16 r squared, or the distance AD is equal to 4r. So all we need to do now is go back to our original triangle ACD and apply Pythagoras once again. So the distance CTD is 2 root 2r. We've just calculated the distance AD as 4r, And so we can say that the distance AC squared, which is the unit cell body diagonal we're looking for, is equal to 4r squared plus 2 root 2r squared. So multiplying out our brackets, we get that this is equal to 16r squared plus 2 squared is 4, root 2 squared is 2, so that's 8r squared. And so AC squared is given by 24r squared, and so AC is equal to the square root of 24r, which simplifies down to 2 root 6r. And so we can give the length of the unit cell body diagonal as 2 root 6r. In part D of the question, you are asked to calculate the molar volume of gold in centimeters cubed per mole. Initially, you might be tempted to try a calculation using the volume of the unit cell calculated in C part 2. However, as we do not know r, the radius of a gold atom, it would not be possible to calculate a final answer. Instead, you need to look back at the start of the question where we were given a value for the density of gold as 19.3 grams per centimeters cubed. The density of a substance is equal to the mass of that substance divided by its volume. So if we apply that equation to 1 mole of gold, we can say that 19.3 grams per centimeters cubed is equal to the mass of 1 mole divided by the volume of 1 mole, or gold's molar volume. Since we know the mass of 1 mole of gold to be 197 grams per mole, we can rearrange the equation to give the volume of 1 mole of gold, or gold's molar volume, as the mass of 1 mole, which is 197 grams per mole, divided by the density of gold of 19.3 grams per centimeters cubed, to give us a final answer for the molar volume of gold as 10.2 centimeters cubed per mole. Part E of the question asks you to calculate what fraction of the volume of the unit cell is occupied by gold atoms. Since from part B of the question we know that each unit cell contains 4 atoms, and if we know that the volume of a sphere is given by the equation 4/3 pi r cubed, then we can say that the volume of the unit cell occupied by atoms is equal to 4 times 4/3 pi r cubed, which is equal to 16/3 pi r cubed. The total volume of the unit cell which contains these 4 atoms was calculated in part C, and we found that it was equal to 16 root 2 r cubed. And so to answer the question, what is the fraction of the volume of the unit cell which is occupied by the gold atoms, we simply need to divide these two values. So the volume of the unit cell occupied by the atoms is 16/3 pi r cubed. The volume of the unit cell which contains these 4 atoms is 16 root 2 r cubed. And so cancelling the r cubes, and indeed cancelling out the 16s, we can calculate the fraction of the unit cell which is occupied by atoms. Part F of the question then requires you to apply your answers to part D and part E to calculate the radius of a gold atom. In part D of the question, you calculated the molar volume of gold to be 10.2 centimeters cubed per mole. In part E then, you found that of this 10.2 centimeters cubed per mole, 0.74 of it was actually occupied by atoms. Knowing this then, we can calculate the volume of 1 mole of atoms to be 0.74 times 10.2 centimeters cubed. And if we do this calculation, we find the volume of 1 mole of gold atoms to be 7.55 centimeters cubed. Since 1 mole of gold atoms contains Avogadro's number of atoms, we can therefore calculate the volume of a single atom of gold by dividing our 7.55 centimeters cubed by Avogadro's number, which is 6.02 times 10 to the 23. And if we do this, we find the volume of a single gold atom to be 1.25 times 10 to the minus 23 centimeters cubed. Finally then, if the volume of a sphere is given by 4/3 pi r cubed, then we know that 4/3 pi r cubed is equal to 1.25 times 10 to the minus 23 centimeters cubed. Solving that equation then for r, we find that the radius of a gold atom to be equal to 1.44 times 10 to the minus 8 centimeters, which is approximately in the scale that we would expect. Part G of the question goes on to look at the application of gold to the Dome of the Rock in Jerusalem. In the introduction to the question, you are told that the Great Golden Dome of the Rock in Jerusalem is a hemisphere of diameter 21 meters, and that the late King Hussein of Jordan donated 80 kilograms of gold to cover the outside of the dome. In part I of the question, you are asked to use this information to calculate the average thickness in centimeters of the gold on the dome. To calculate the thickness of the gold on the dome, you need to divide the volume of the gold by the surface area to be covered. Since we know the density of gold to be 19.3 grams per centimeters cubed, then we can calculate the volume of 80 kilograms of gold by dividing this mass in grams by the density in grams per centimeters cubed. And if we do that calculation, we find that the volume of 80 kilograms of gold is 4,145 centimeters cubed. To calculate the surface area to be covered by this gold, we need to use the equation given in the question for the surface area of a sphere, which is 4 pi r squared. The dome shape is a hemispherical, and so the surface area of the dome is a half of this 4 pi r squared. In the question, we're given that the diameter of the hemisphere is 21 meters, and so we know that the radius must be half of that, or 10.5 meters. However, since we've been calculating the volume of the gold in centimeters cubed, it's probably best at this stage to use our radius in centimeters, and so the radius of the hemisphere becomes 1,050 centimeters. So if we substitute that radius into our equation for the surface area of the dome, we find that the surface area of the dome is equal to 1/2 times 4 pi times our radius of 1,050 centimeters all squared. And if we do that sum, we find that the surface area of the dome is a massive 6,927,211 centimeters squared. So we now know the volume of the gold which is going to be coating the dome and the surface area to be covered, and so we can simply put those numbers into our equation at the top there to calculate that the thickness of gold on the dome is equal to 4,145 divided by 6,927,211, which gives a value for the thickness of the gold on the dome as 5.98 times 10 to the minus 4 centimetres. However, we cannot give this final answer to this high degree of accuracy. If we look back at the question, we are basing this answer on two values which are given to two significant figures: the mass of gold used of 80 kilograms and the diameter of the hemispherical dome of 21 meters. And so our final answer for the thickness of gold on the dome must be given to only two significant figures, which is 6.0 times 10 to the minus 4 centimeters. In part 2 of the question, you are then asked to use this value to calculate the average number of layers of gold atoms covering the surface of the dome. If we look back at the introduction to part G, we are told that the most efficient way of stacking layers of gold atoms has 3 layers in the length of the unit cell body diagonal, and therefore that the thickness of one layer is 1/3 of the distance from A to C. Looking back at our answers to the previous parts of the question, we've calculated much of the information we need to answer this question previously. In C part 3, we calculated that the length of the unit cell diagonal was given by the equation 2√6r. And in part F, we calculated that the radius of the gold atom, r, was 1.44 times 10 to the minus 8. Therefore, if we know that the thickness of one layer of gold atoms is given by 1/3 of the length of the unit cell diagonal, we can calculate that the thickness of one layer of gold atoms is equal to 1/3 times 2√6 times r of 1.44 times 10 to the minus 8. And if we do that calculation, we find that the thickness of one layer of gold atoms is 2.35 times 10 to the minus 8 centimeters. So we now know the thickness of gold on the dome as 6.0 times 10 to the minus 4 centimeters, and that each individual layer of gold atoms has a thickness of 2.35 times 10 to the minus 8. And so we can say that the average number of layers of gold atoms covering the surface of the dome is the thickness of the gold, which is 6.0 times 10 to the minus 4, divided by the thickness of one layer of gold atoms, which is 2.35 times 10 to the minus 8, which gives us a value for the average number of layers of gold atoms covering the surface of the dome of 25,446, or sticking with our degree of accuracy of two significant figures, is 25,000.